Early 1916 found Nissen, a Canadian-born mining engineer with the Royal Engineers, inspecting construction zones near EPI, their grounds churned to mud. Architectural theory held no place in his thoughts, only the urgent need to shelter British soldiers dying from exposure in canvas tents collapsing under snow. The Western Front had consumed traditional building methods. Timber was scarce, skilled carpenters were in the trenches, and every structure required resilience against shelling. For months, Nissen had observed abandoned corrugated iron sheets, intended for roofing but piling up near supply depots as no one knew how to utilize them. What made Nissen's approach revolutionary wasn't elaborate engineering. The breakthrough lay in ruthless minimalism. Nissen's revolutionary approach centered on a simple yet ingenious solution. He bent standardized corrugated metal sheets into a half-cylindrical form, creating a self-supporting structure requiring no internal bracing. In March 1916, a team of 6 inexperienced soldiers assembled the first prototype at EPRA in under 4 hours, using only basic tools. When Nissen presented this design to British Army Command, his key assurance proved transformative. Any infantry soldier could erect the huts in 3 days, with all materials transported on a single truck. The Army promptly tested this concept at Richborough Port in April 1916, where the 172nd Tunneling Company constructed 20 huts, each measuring 16 feet wide and utilizing approximately 600 square feet of corrugated steel. The curved shell design deflected rain and shrapnel, eliminating vulnerable points where projectiles could catch and tear. By June 1916, Nissen huts had proliferated across the British sectors of the Western Front. That August, the War Office placed a massive initial order, 10,000 units to be manufactured and delivered before winter. What made Nissen's approach revolutionary wasn't merely its speed, but the elimination of skilled labor from the construction process. Conventional military buildings demanded carpenters, masons, and engineers. In contrast, Nissen's design required none of those specialized tradespeople. The pre-drilled corrugated metal sheets came with holes spaced at precise 14-inch intervals. Prefabricated wooden end panels arrived ready for assembly. The foundation itself was optional. Crews could simply bolt the hut directly to wooden sleepers or even packed earth if needed. A small squad of soldiers could rapidly assemble the materials, establish the foundation, and weatherproof the structure before nightfall. During the Battle of the Somme in late 1916, construction crews erected Nissen huts within range of artillery fire, providing immediate shelter for wounded troops evacuated from the front lines. The hut's dimensions reflected meticulous planning for maximum efficiency. Its 16-foot width allowed for 2 rows of bunks with a central walkway, accommodating 30 men comfortably or 50 in emergencies. The curved roof, rising to around 15 feet at the apex, offered ample headroom for soldiers to stand upright throughout the interior. Ventilation came from adjustable panels at each end, and the corrugated steel's natural gaps prevented the condensation issues that plagued canvas tents. The Armistice of November 1918 saw the British military deploy over 100,000 Nissen huts across Europe, the Middle East, and Africa. These versatile structures served as barracks, hospitals, supply depots, and command posts, providing instant infrastructure wherever the Army required it. The design documentation Nissen submitted to the War Office in April 1916 revealed the innovation behind his hut's superior performance. Conventional military buildings relied on intricate framing of vertical posts, beams, and trusses, requiring meticulous cutting and joining. Nissen, however, eliminated the need for framing altogether. His curved, corrugated metal sheets were self-supporting, with the walls and roof comprising a single integrated component. Bolting one sheet to the next not only added coverage but also generated structural integrity. The Nissen hut's ingenious design centered on simplicity and efficiency. Each 16-foot panel overlapped the previous one by 3 inches, with bolts penetrating the triple-layered metal junctions to form a continuous, load-distributing shell. The construction process prioritized foolproof execution. Crews first laid wooden base plates in a rectangular outline, then bolted vertical wooden ribs to those plates at 7-foot intervals. Next, they attached the initial corrugated sheet to the ribs and bolted it to the base. Subsequent sheets overlapped and connected to the previous ones, repeating until the half-cylinder structure was complete. Finally, workers installed the wooden end walls, pre-fitted with doors and window frames. An experienced crew could assemble the entire structure in just 72 hours, while even green troops required only 4 to 5 days. Throughout the summer of 1916, the British Army rigorously tested this process at training camps in Dover and Southampton, timing different units to establish reliable deployment schedules. Early 1916 found Nissen inspecting construction zones, their grounds churned to mud. Architectural theory held no place in his thoughts. What made Nissen's approach revolutionary wasn't elaborate engineering. The breakthrough lay in ruthless minimalism. Nissen designed the corrugated steel sheets to align with Britain's wartime production capabilities. The 26-gauge metal proved sturdy yet light enough for 3 men to maneuver a 16-foot section without machinery. Precise curve calculations ensured standard sheet metal rollers could form the shape without retooling. Nissen further streamlined assembly by specifying 7/16-inch bolts, the same size used in shipbuilding, simplifying supply chains. Wooden components like end walls, base plates, and interior ribs could incorporate whatever local timber was available, whether pine, oak, or salvaged materials. This field adaptability rendered the Nissen hut system nearly universal. In Mesopotamia during 1917, British forces built Nissen huts without the customary wooden end walls, instead utilizing bricks scavenged from the ruins of local villages. Meanwhile, in Egypt, engineering units positioned the bases directly on the sand and used interior poles cut from nearby palm trees rather than milled lumber. Yet the core principle remained unchanged. Those curved, ridged metal sheets would form a weatherproof shell regardless of the surrounding construction details. March 1917 witnessed a Canadian unit at Vimy Ridge erecting a Nissen hut amidst active bombardment, working in 30-minute shifts between artillery barrages. The structure became operational within 18 hours, immediately housing 40 wounded men evacuated from the ridge assault. The speed advantage of this modular design proved most evident in logistics. A single railway flat car could transport enough materials to assemble 8 complete Nissen huts. The military camp in France witnessed a relentless construction pace throughout 1917. Teams erected 1 Nissen hut every 6 hours, working in shifts. By October, the sprawling facility accommodated 100,000 troops, the majority housed in these prefabricated structures. The hospital section alone contained 300 huts, providing beds for 12,000 patients. When the German spring offensive struck in March 1918, requiring shelter for 20,000 additional wounded, crews swiftly assembled 70 new hospital huts in just 11 days. Across the Atlantic, the United States Navy dispatched its first engineering assessment team to Britain in September 1940, 15 months before the Pearl Harbor attack. Commander George F. Dorat, stationed at the Bureau of Yards and Docks in Washington, had explicit instructions: study British temporary construction methods and determine their suitability for supporting American military expansion. Dorat's 6-week tour of British military facilities across England and Scotland culminated in a classified November 1940 report. Spanning 18 pages, this document detailed the Nissen hut's assembly times, material specifications, and insights from construction officers who had deployed the structures since 1916. Dorat's assessment was unequivocal. The Nissen hut represented the most rapidly constructed field structure ever conceived. However, he concluded that American forces would require modifications. These adaptations commenced immediately after the Pearl Harbor attack on December 7, 1941. The Navy Civil Engineering Corps selected Quonset Point Naval Air Station in Rhode Island as the development site, owing to its active construction projects and direct rail access for shipping prototypes. Commander John Barney Cyrus oversaw the design team tasked with translating the Nissen hut specifications Doria had brought from Britain, along with the actual blueprints provided by the British government under Lend-Lease arrangements. The first American prototype emerged in February 1942, bearing a resemblance to the Nissen but incorporating fundamental differences that would shape every subsequent unit. American engineers revised the structural logic, replacing Nissen's self-supporting corrugated sheets bolted directly together with an internal steel framework. This framework consisted of curved steel arches, essentially ribs formed from steel channels, that stood independently and supported the corrugated panels. The panels no longer carried structural loads, instead serving as cladding attached to the frame with self-tapping screws rather than through bolts. Cyrus advocated this design approach, arguing it would yield sturdier structures capable of supporting heavier equipment and providing more robust anchor points for electrical and plumbing systems. His assessment proved accurate on both fronts, but the added complexity conflicted with Nissen's deliberate simplicity. The framework requirement meant the prefabricated huts arrived on site as more components requiring more assembly steps. A standard 40-foot Quonset, for instance, needed 14 steel arch ribs, each weighing roughly 90 pounds, positioned at specific intervals and bolted to foundation plates. Only after the frame was complete could crews attach the corrugated panels. In contrast, Nissen's assemblies began with the panels themselves, building outward. This philosophical difference, frame first versus panels first, added between 12 and 18 hours to construction time, based on tests conducted at Quonset Point in March 1942. Navy leaders embraced the trade-offs, prioritizing lasting infrastructure over rapid deployment. American strategic planning presumed most bases would serve for years, not weeks. The Quonset design incorporated features absent from Nissen's model. Insulation became standard, with fiberglass sandwiched between steel panels and interior plywood. Electrical conduits integrated into the framework during assembly, rather than surface-mounted afterward. Wooden floors replaced packed earth or duck boards. Windows grew larger and included screens. Doors utilized American standard hardware instead of British hinges and latches. Each enhancement improved comfort and functionality, yet also added weight, components, and assembly time. The Quonset hut package proved approximately 30% heavier than equivalent Nissen materials, necessitating more transportation assets like trucks or railcars. By May 1942, the Navy had standardized 3 distinct Quonset sizes, 20 feet, 40 feet, and the largest at 50 feet wide. Production contracts went to experienced prefabricated steel constructors, the George A. Fuller Company and Strand Steel Corporation, with the first mass-produced units shipping to naval stations in June 1942. The steel framework defining the Quonset design introduced a parts dependency the Nissen hut never faced. Each arch rib arrived as a preformed steel channel, bent to the precise radius required for that particular hut size. If any single rib suffered damage during shipping, bending, cracking, or missing bolt holes, the entire frame's geometry could fail catastrophically. In contrast, Nissen huts tolerated imperfections, as the corrugated panels flexed and adjusted as crews assembled them. The corrugated panels themselves resolved minor alignment issues. Crews had to precisely position the Quonset ribs before installing any exterior components, spending hours using levels, plumb lines, and measuring tapes to ensure each rib stood at exactly 90 degrees to the foundation and matched the spacing templates. The escalating bolt count reflected the growing complexity. A standard 16-foot Nissen hut required around 200 bolts, primarily connecting the corrugated panels to each other and the wooden base. In contrast, a 40-foot Quonset hut needed over 700 bolts and screws. 14 arch ribs bolted to foundation plates used 6 bolts each, totaling 84, while the cross-bracing between ribs added another 100 fasteners. Attaching the corrugated panels to the framework with self-tapping screws meant 16 screws per panel, amounting to roughly 30 panels for a 40-foot Quonset. The interior assembly process followed. Plywood lining attached to the ribs, insulation fasteners installed, electrical boxes mounted, and floor joists bolted to the foundation. Each additional fastener presented another potential source of construction delays when tools broke or hardware went missing in the field. American production methods emphasized standardization, which paradoxically reduced flexibility for on-site adjustments. Quonset components were manufactured to tight tolerances in stateside factories, ensuring perfect fit under controlled conditions. However, combat zones lacked such control. When the 804th Engineer Aviation Battalion reached Henderson Field on Guadalcanal in January 1943, they found that humid conditions during the Pacific crossing had caused some steel ribs to rust at the bolt holes. These precisely formed arches were integral to the structure, so the rusted ribs could not be modified or replaced with local materials. The engineers endured a 3-week wait for replacement ribs from Pearl Harbor while troops camped in tents. Though the insulation system provided superior comfort, it became a construction bottleneck. Quonset specifications mandated installing fiberglass batting between the corrugated exterior and interior plywood lining, necessitating a 3-stage process. Erect the frame, attach exterior panels, then return inside to install insulation and interior walls. In contrast, Nissen huts allowed single-stage construction. Once the corrugated panels went up, the structure stood complete and habitable, with interior improvements added later if time and resources permitted. At the Navy's Camp Endicott training facility in Davisville, Rhode Island, CB Battalion instructors timed both systems in 1943. The Nissen hut's streamlined design enabled rapid field assembly. An experienced team could erect one in just 2 days. By contrast, a comparable Quonset structure, with its comprehensive insulation and interior finishes, required twice as long, at 4 days. The Quonset's integrated conduit system also introduced an additional layer of logistical complexity, necessitating electrical work to proceed concurrently with construction rather than sequentially. However, this parallel approach proved advantageous at naval air stations with ample electrical contractors on hand. The 6th Naval Construction Battalion stationed in the Solomon Islands relayed in April 1943 that electrical work obstructed timely project completion by 2 days on average. With qualified electricians rotating between multiple construction sites, their presence on the floor system assembly created scheduling conflicts in forward combat zones with limited personnel. Nissen huts lacked integrated floors, requiring troops to lay temporary wooden duckboards or pour concrete after the main structure was erected. However, the specified floor system, pressure-treated joists, plywood subflooring, and finished wood flooring, installed during initial construction maintained the interior's cleanliness and comfort. This comprehensive flooring solution, though, added an entire phase of carpentry work to the overall assembly process. When the Western Task Force led by Major General George Patton landed near Casablanca on November 8, 1942, supply officers carried orders to immediately construct camps for 35,000 troops. The invasion plan had allocated space for Quonset huts shipped from Virginia, but combat conditions forced field commanders to make calculations the Navy hadn't tested at Quonset Point. Lieutenant Colonel Paul Thompson, commanding the 16th Engineer Battalion, observed his crews grappling with the steel framework in sand that refused to hold anchor bolts. The foundation plates, designed for firm ground or concrete pads, twisted when tightened because the Moroccan coastal sand compressed unevenly. Thompson's December 1942 after-action report noted that his crews required 4 days per Quonset hut, with the majority of time lost stabilizing foundations and shimming framework ribs to compensate for uneven settling. The British forces in the North African theater simultaneously deployed Nissen huts shipped from Alexandria. On November 12, 1942, the 512th Specialist Team of Royal Engineers set up a field hospital outside Alers. Working with local Algerian laborers with limited English proficiency, the team completed 16 Nissen huts in just 9 days. Their innovative approach eliminated the need for foundations. Instead, they laid railway sleepers directly on graded sand, bolted the corrugated metal panels to the sleepers, and stabilized the structure with sand berms piled against the exterior base. When late November windstorms struck, several partially constructed Quonset huts toppled due to their unfinished frameworks. In contrast, the fully assembled Nissen huts, with their self-supporting shells, remained standing. The Pacific Theater later exposed even starker differences, as evidenced on Guadalcanal. The 1st Marine Division received Quonset huts in February 1943, after months of battling the elements in muddy tent encampments. Gunnery Sergeant Robert Leckie, whose memoir chronicled the campaign, described construction crews toiling in 100-degree heat with 80% humidity. By mid-morning, the steel framework components had become too hot to handle with bare hands. Crews worked abbreviated schedules, from dawn until 10 a.m., then again in the evenings until dark, a shift that stretched 5-day construction estimates into 2-week realities. Concurrently, Australian forces supporting operations from Port Moresby utilised Nissen pattern huts manufactured in Sydney. Australian war production records indicate these simplified versions eliminated even the wooden end walls, employing corrugated steel throughout. Construction teams reported average assembly times of just 36 hours. Rapid base expansion made timing a critical factor. When Admiral Chester Nimitz ordered the development of Fufuti Atoll in the Ellis Islands during March 1943, Navy planners faced a 60-day deadline to house 5,000 personnel. The 2nd Naval Construction Battalion arrived with both Quonset materials and some British Nissen huts obtained through Commonwealth supply channels. Battalion Commander Lieutenant Commander Joseph Blondin split his crews to test both systems under identical Coral Atoll conditions. Blondin's official report in May 1943 provided precise data. Nissen huts averaged 54 hours from first foundation timber to completed structure, while Quonset huts averaged 91 hours. A gap attributed primarily to framework alignment and interior finishing requirements. This speed differential proved critical during emergency expansions. Following the Battle of Midway in June 1942, the Navy urgently required increased hospital capacity at Pearl Harbor for incoming wounded. The hospital's existing capacity proved insufficient to meet surging demand. Construction battalions thus erected temporary ward buildings adjacent to the main facility. While Quonset huts with their required foundations, frameworks, and interior systems would have necessitated a 2-week timeline, crews instead adopted a hybrid approach. Nassen-style corrugated shells, erected in just 3 days, received subsequent installation of interior medical equipment. These emergency wards remained operational through 1944, accommodating over 2,000 patients. However, the weather resistance of this solution revealed unexpected trade-offs. Quonset insulation maintained comfortable interior temperatures despite extreme heat and cold, yet the complex wall assembly created moisture traps. In the perpetually foggy, rainy Aleutian Islands during 1943, insulated Quonset huts developed condensation between the exterior steel and interior plywood, leading to rust and mold. Nissen's single-layer, naturally ventilated huts, while less comfortable, proved more effective at moisture control. However, American industrial capacity transformed the Quonset into a mass-produced phenomenon that the handcrafted Nissen design could not match. By mid-1943, the Strand Steel Corporation's Indiana factory churned out 200 complete Quonset packages daily, shipping them nationwide for Pacific and European deployment. Pennsylvania's George A. Fuller Company added another 150 units per day. This staggering annual output exceeding 100,000 huts demanded rigid standardization. Every component had to be perfectly interchangeable, with a steel rib manufactured in January 1943 fitting seamlessly with panels and hardware produced 18 months later. American factories achieved this precision through die forming and jig-based production, capabilities the British cottage industry never approached in Nissen manufacturing. The standardization philosophy extended beyond physical dimensions alone. Quonset huts came in precisely 3 widths, 20, 40, and 50 feet, with lengths in 10-foot increments. This modular approach allowed logistics officers to calculate shipping requirements with exactitude. A standard 40-foot flatbed could carry 1 complete 40 by 20 package. Transport ships allocated cargo space in Quonset unit increments. Supply depots stocked replacement parts, secure in the knowledge that any 20-foot arch rib fit any 20-foot hut, regardless of when or where either was manufactured. This system eliminated the improvisation that made Nissen huts flexible but also inconsistent. Cost accounting revealed where American engineering priorities diverged from British expediency. In 1943, the U.S. Navy paid around $850 for each complete 40 by 20-foot Quonset hut, covering all materials, hardware, insulation, electrical components, and flooring. By contrast, a comparable Nissen hut cost approximately $230 in inflation-adjusted 1943 currency, based on British production records from 1918. While the Quonsets' superior comfort and electrical systems justified the higher price, the 300% cost increase mattered greatly when multiplied across thousands of units. The total American expenditure on Quonset production exceeded $140 million by war's end. Production volume numbers, however, told a different story. The United States manufactured roughly 170,000 Quonset huts between 1941 and 1946, averaging 34,000 per year. In contrast, Britain produced around 100,000 Nissen huts solely during World War I, from 1916 to 1918, at an average rate of 50,000 per year. A remarkable feat given Britain's more limited industrial infrastructure at the time. The distinction didn't lie in production capacity. The breakthrough centered on architectural simplicity. Nissen's huts demanded only basic materials, corrugated steel panels, rudimentary fasteners, and rough-sawn timber. Any sheet metal workshop could fabricate the components. In contrast, Quonset structures required specialized engineering, curved steel ribs, precision die cutting for panel attachment points, and coordination between insulation, electrical, and lumber suppliers. These technical complexities became most apparent in adaptability. After initial erection, Quonset huts could undergo extensive modifications. Crews could add partition walls, install heating systems, run supplementary electrical circuits, and mount heavy equipment to the steel frame. These capabilities made them suitable for permanent installations like stateside training bases and rear echelon headquarters. The Naval Air Station Alameda in California received over 400 Quonset huts in 1943, which served as workshops, classrooms, and administrative offices. Many of these structures remained in use until the base's closure in 1997, some for over half a century. This longevity validated the American approach for installations where permanence took precedence over rapid construction. However, the framework enabling those upgrades became a liability when used in temporary field settings. In June 1943, the 43rd Infantry Division's relocation from Guadalcanal to New Georgia proved problematic. The steel ribs of their Quonset huts, once bolted together, were difficult to separate without damaging the threads. Similarly, the screwed-on panels could be removed, but without the framework, they were rendered useless. Consequently, the entire camp infrastructure, 42 Quonset huts, had to be abandoned in place. The Nissen hut's modular design allowed for rapid assembly and disassembly, with the bolted panels separating cleanly for reuse elsewhere. British forces routinely relocated these portable structures, moving the same Nissen camps from Egypt to Italy to Greece as front lines shifted. However, the true divergence between the Nissen and Quonset legacies emerged not during wartime, but in the decade following. When World War II concluded in August 1945, the U.S. military found itself with approximately 70,000 surplus Quonset huts scattered across domestic bases that were rapidly closing. The War Assets Administration, tasked with liquidating military surplus, began selling complete Quonset huts to civilians in 1946 at prices ranging from $200 to $600, depending on size and condition. That same year, over 15,000 Quonsets were purchased by farmers, small businesses, and housing-strapped families across America. The Nissen huts' integrated floors, insulation, and electrical systems rendered them immediately habitable as homes, workshops, or storage facilities. This civilian adoption catalyzed an American architectural phenomenon that persisted for decades. Today, one can still observe numerous Nissen huts serving as machinery sheds and grain storage across the rural Midwest. Small airports in the region utilized these structures as hangars through the 1970s. The University of Illinois housed returning veterans in a Quonset village from 1946 until 1972 to 260 huts providing temporary family housing that became semi-permanent, as nothing replaced them. The structures succeeded in civilian use precisely because of the features that had slowed their battlefield deployment. The insulation maintained comfortable year-round conditions, while the sturdy framework supported shelving, equipment hoists, and other modifications. The completed interiors readily accepted drywall and paint for those desiring conventional aesthetics. In contrast, Britain's approach to Nissen huts after 1945 involved active removal. The military viewed them as symbols of wartime hardship and sought their elimination. Thousands underwent dismantling, with the corrugated panels sold as scrap metal during the post-war steel shortage. Some found civilian applications, as farmers in Yorkshire and Scotland converted them into sheep barns and equipment storage facilities. Yet the British government actively discouraged private retention, wishing to distance the national identity from wartime temporary architecture. By 1955, the majority of Nissen huts had vanished from Britain, except on remote military ranges and agricultural properties where practicality outweighed appearance. Today, the few surviving examples either serve as preserved historical artifacts or remain hidden on private land, where owners prioritize their weatherproof storage capacity over aesthetic considerations. The architectural elite dismissed these designs, their scorn betraying class-based biases against makeshift structures. American architectural journals in the 1950s rarely acknowledged Quonset huts, except to condemn them as visual blight. Famously, Frank Lloyd Wright derided them as metal pig shelters unfit for human habitation. British architects proved even harsher, with a 1948 Royal Institute of British Architects publication describing Nissen huts as corrugated embarrassments that should be swiftly removed from the landscape, as economically feasible. This professional hostility overlooked the practical reality that both designs had provided effective, economical shelter to millions when no alternatives existed. Commonwealth nations developed their own variants, often returning to Nissen's core principles. Australia's post-war reconstruction saw the adoption of streamlined curved roof huts, a departure from the intricate American framework. These structures, prioritizing speed and cost over comfort, served as immigrant housing and remote infrastructure throughout the 1960s. Concurrently, Canada's Department of National Defence continued manufacturing Nissen pattern huts for northern bases, where extreme cold rendered insulated Quonset huts impractical. The single-layer metal construction prevented the catastrophic ice damming that plagued pitched roofs when snow loads exceeded design limits. However, both designs eventually fell out of favor as military housing needs evolved. By the Vietnam War era, the United States had developed modular containerized housing, capable of rapid helicopter transport and assembly, outpacing even the efficiency of Nissen huts. These systems utilized lightweight aluminum frameworks and fabric panels, a stark contrast to the steel construction of earlier models. The Nissen hut's ingenious design revolutionized military shelter. Compared to today's high-tech container systems costing $50,000 or more, Nissen's 1943 Quonset solution came at a mere $850 per unit. Even accounting for inflation, modern shelters run roughly 6 times the cost per square foot while offering comparable functionality. The key lesson lies in recognizing that military logistics don't always benefit from elaborate engineering. Peter Nissen's breakthrough stemmed from a simple question: what's the bare minimum needed to keep soldiers dry and alive? His answer, curved corrugated metal panels bolted together, defied conventional construction principles. No foundations, no framing, no skilled labor, just prefabricated sheets and fasteners. The Nissen hut's ruthless simplicity allowed a sergeant and 5 exhausted infantrymen to construct shelter within 72 hours, even under artillery bombardment. In contrast, the American engineers behind the Quonset asked a different question: how to make the structure more comfortable and permanent. Their answer delivered objectively superior architecture, yet proved less practical as emergency shelter. This tension between optimal and adequate solutions recurs throughout military history. The M1 Garand rifle outperformed the bolt-action Springfield in every metric, yet also weighed more, featured greater complexity, and demanded heightened maintenance. Similarly, Sherman tanks demonstrated mechanical reliability, though underarmed compared to German Panthers. American forces ultimately prevailed through adequate equipment deployed in overwhelming numbers, rather than perfect hardware deployed slowly. The Quonset followed this pattern, and improved shelter over the Nissen, but won armies required with greater urgency than enhanced quality. The Marine Division's 1942 Guadalcanal campaign underscored the primacy of rapid shelter over refined amenities. As the troops grappled with the mud of late that year, a weatherproof structure completed within 3 days would have proven far more valuable than an insulated, electrified facility requiring 10 days. This speed over quality calculus, a constant imperative of World War II, has largely faded from modern military doctrine. Current U.S. construction standards presume infrastructure will precede major deployments, supply lines will remain secure, and building can occur unimpeded by enemy action. These assumptions held true in Iraq and Afghanistan, where American forces dominated the skies and enjoyed months to construct forward operating bases. The Marine Corps recognized this gap 2 years ago, reintroducing expeditionary advanced base operations, a reminder that rapid deployment outweighs creature comforts. This engineering mindset extends past military applications. Modern construction everywhere prioritizes complexity over simplicity. Building codes compel electrical systems, insulation standards, foundation specifications, and numerous other features improving structures, yet impeding their speed and expense of assembly. Reasonable for permanent buildings, but troublesome for emergency relief efforts. After Hurricane Katrina in 2005, FEMA desperately needed immediate shelter for thousands of displaced residents. Manufactured dwellings offered temporary housing, yet demanded concrete foundations, utility hookups, and weeks per unit to install. In contrast, Nissen-style structures could arise within days, relying solely on the devastated area's existing infrastructure, providing immediate shelter while permanent reconstruction progressed. America's production of 170,000 Quonset huts represented genuine industrial achievement, sheltering millions of personnel across every theater. These semi-permanent base structures served their intended role well, yet failed to match the feat of 6 British soldiers in 1916. Building weatherproof shelter in just 3 days, using only hand tools and determination, embodied the true innovation, capability, speed, and brutal simplicity. The Quonset improved upon the Nissen in every aspect except the one that mattered most in combat. Soldiers' urgent need for shelter from impending bombardment drove the design philosophies behind 2 distinct hut models. Across former military sites, the enduring presence of corrugated, curved American Quonsets attests to their engineering durability, outlasting their original purpose. In contrast, the vanished British Nissen huts, though simpler to construct under any conditions, were readily abandoned as front lines advanced. Both solutions fulfilled the essential function, but only the Nissen approach enabled rapid, on-demand assembly amidst active combat. This distinction between architectural merit and battlefield exigency defined their divergent legacies.